Hey everyone, welcome to Physics Lab Podcast. I'm Amara, and today we're diving into one of the most fundamental laws of physics, Newton's second law. If you've ever wondered why it's harder to push a heavy car than a light bicycle, or why a stronger push makes things move faster, you're about to find out.
I'm Marcus, and I'm excited to break this down with you. Newton's second law is expressed as F equals ma, where F is the net force applied to an object, m is its mass, and a is the acceleration it produces. Basically, it tells us that force and acceleration are directly proportional, while mass and acceleration are inversely proportional.
Exactly. Let's think about this practically. Imagine you're on a skateboard. If someone gives you a gentle push, you accelerate slowly. But if they push harder, you accelerate faster. That's the force-acceleration relationship. Now, if you're carrying a heavy backpack while on that skateboard, the same push won't accelerate you as much. That's where mass comes in.
Great analogy, Amara. Now, in our lab experiment, we're testing this law using a PAS car dynamics system. We have a cart on a track, a force sensor attached to it, and a motion sensor to measure movement. We also use a hanging mass connected by a string over a pulley to create a controlled force.
A scientific method is crucial here. We start with a hypothesis. If we increase the force on the cart while keeping its mass constant, the acceleration should increase proportionally. Then you design an experiment to test this. We collect data by running the cart multiple times, each time adding more mass to the hanging weight, which increases the force.
During each run, the capstone software records two important graphs, a velocity time graph and a force time graph. From the velocity time graph, we calculate acceleration by finding the slope of the line. Remember, acceleration is the change in velocity divided by the change in time. The steeper the slope, the greater the acceleration.
And from the force time graph, we determine the average force applied during that run. We record both values in our data table. We repeat this process 5 times, increasing the hanging mass by 5 to 10 grams each time. This gives us multiple data points to work with.
Once we have all our data, we move to the analysis phase. We plot force on the vertical axis and acceleration on the horizontal axis. If Newton's second law holds true, we should see a straight line passing through our data points. The slope of this line is incredibly important because it represents the mass of the cart and force sensor combined.
That's the beautiful part. By using the mathematical relationship F equals ma, we can rearrange it to m equals F divided by a. So the slope of our force versus acceleration graph directly gives us the mass. We can then compare our calculated mass to the actual measured mass and calculate the relative error.
The relative error calculation shows us how accurate our experiment was. It's calculated as the absolute difference between our experimental mass and the actual mass, divided by the actual mass, then multiplied by 100 to get a percentage. A smaller percentage means our experiment was more accurate.
Throughout this experiment, we're applying the scientific method at every step. We observe that objects accelerate when forces are applied. We form a hypothesis based on Newton's law. We design a controlled experiment with variables we can measure precisely. We collect quantitative data using sensors and software.
Then we analyze that data by creating graphs and calculating values. We look for patterns and relationships. Finally, we draw conclusions about whether our data supports Newton's second law. If our results show a linear relationship between force and acceleration, we've successfully validated the law experimentally.
It's important to note that real experiments always have some error. Friction on the track, air resistance, and measurement uncertainties all affect our results. That's why we take multiple measurements and calculate averages. Science isn't about getting perfect results. It's about understanding the principles and recognizing sources of error.
Absolutely. Before you start the lab, make sure your track is level, your sensors are properly calibrated, and you understand how to use the capstone software. Zero the force sensor before each run, and be careful not to let the cart crash into the pulley. Safety and precision are key to good data.
As you work through this experiment, think about how Newton's second law applies to the real world. It explains why seatbelts are important in cars, why rockets need powerful engines, and why professional athletes train to increase their strength and power. Physics isn't just theory, it's everywhere around us.
Thanks for joining us on Physics Lab Podcast. We hope this episode helped you understand Newton's second law and the experimental process. Remember, science is about asking questions, testing ideas, and learning from data. Good luck with your lab, and keep exploring the physics that shapes our universe.
See you next time on Physics Lab Podcast.